These are its characteristics, shall we say. All right, let's take this out of here. And that's the end of that video segment. We're going to start the third one. Questions, comments? Okay, let me simply say, just to review the bidding here, the moment of inertia matrix is 3 by 3. It's got 9 numbers in it. You'll find out shortly here. Oh, and they are referred to symbolically thusly. You notice again, Larry, I hope you can read. This is one I should have asked you about. Can you read that? That's IZZ. Just barely. Okay. Anyway, the 9 numbers that comprise the moment of inertia matrix have symbolic names IXX, IXY, IXZ. And the way you read this is that it tells you what this essentially is, what the moment of inertia of the object is with respect to its x-axis. This is the moment of inertia of the object with respect to its y-axis. Okay, and we're talking little y here, little x and little y, the body coordinate system. And let me simply say another thing you can see just by looking at this is you see the similarities here. Look at this. Okay, does everybody see the similarity in that? Anyway, you'll see in a moment the moment of inertia matrix is symmetric as well. All right, because see these product terms, m sub I xy, m sub I xy. Okay, so these off-diagonal terms are all identical. So there's really only 6 numbers that matter. You can either take those 6 or this 6, and that'll do it. Okay, so with that, and this is the beginning of the next video segment. Okay. You can't read that? Say it again?
Extra 0, you can withdraw 4.
What are you missing?
Here.
Point taken. Thank you. As if they were playing musical chairs or something and the music stopped. Little zeros are fighting. Anyway, there's 9 places to be in this matrix, okay? And when, let me simply say it is always possible, interestingly enough, you pick the object, doesn't matter how complicated it is, there is always some choice of directions for this body coordinate system for which the moment of inertia matrix is diagonal. That is to say, the only non-zero elements lie on the diagonal and all the off-diagonal terms are zero. And, oh, I can't do anything with these. These are called okay, these are called the principal directions. Okay, whatever those, and there's whatever those are, that one that causes this to be the case is the principal axes, and those define the principal directions. Fair enough? And just for some terminology, these guys have the name principal moments of inertia. All right, now what I'd like to do is, let me erase all this. You guys stand up and talk to yourselves while I erase the boards. Take a little break. Okay. All right. Oh, there you go. Well, they're still here. You're still here. Excellent. Very good. What I'd like to do quickly is do some examples, or show you some examples. These are right out of your book. The sphere is kind of, and what I'm going to do here is I'm going to draw little, in each case, I'm going to draw little x, little y, little z, and little 0, or little o, I should say. I'm drawing the body coordinate system, and this is an artfully drawn sphere of mass m and radius r. And if you go to the book and check this out, or excuse me, this would be, let me do this. It's allow me to attempt at clarity here. The body coordinate system's origin, I'm going to choose the center of mass to be the center of the body, or the origin of the body coordinate system. If you will, you still get to choose the directions, but the center of mass is that. And let me say this, for the sphere, okay, this one is about as simple as they get. It is diagonal. There are non-zero terms only on the diagonal, and they're the same. Doesn't matter whether you spin this thing about the little x-axis, the little y-axis, or the little z-axis, you get this, the object looks the same. Its moment of inertia is about that axis is 2/5 mr squared. And let me just make it clear, it should be already, that this nasty looking evaluation process, you know, you got to take all the points and take their x and y and z values with respect to the body coordinate system, sum them all up. That turns into an integral, okay? Math PhD students over 50 years have generated quite a collection of these calculations for regular geometric figures. All righty? This is the first one. Let me see if I can squeeze another in here. This is the cylinder. And once again, this is little x, little y, the center of mass. All right, and the answer here, this is G. There's R and H clearly labeled there. And the last one is okay. I'll give you a chance to copy that down, and then we'll discuss these a little bit. All right. And again, these are in your book. No need to work too hard at capturing this. It's more important that you understand what's going on. Let me just let me make a subtle point here. In fact, it's not such a subtle point. With few exceptions, we're never going to ask you to evaluate this for really complicated objects. All righty? I mean, you might be called upon to evaluate this for a point mass or two or something like that. But anytime you get into serious geometry, if you ever find yourself saying, "Oh my God, how am I going to?" Don't do it. All righty? If it's a regular geometric shape, like a sphere, a cylinder, a slender rod, a disc, a flat plate, stuff like that, there are tables in your book where these things are derived. And I'll show you right now. Any guys taking 2007? Oh, guess not. Well, never mind. How about SolidWorks? Anybody ever heard of SolidWorks? Did I tell you? My students founded the company. Yeah, absolutely. I didn't make any money, but they did. hang on one second. This is for those of you who are SolidWorks users. Somebody came up after class and asked me this. Anybody recognize that? That's a SolidWorks screen. It happens to be a slender rod. Okay? Anyway, like all I'm saying, anytime, if you're going to build something, you say, I really need to know, after what they taught us in 203, I really need to know what the moment of inertia is for this widget, for this really complicated widget. But how on earth will I ever do that? Okay, the answer, bink, press that button. All right? Model the object in SolidWorks. It can be arbitrarily complex, no joke. It can be a Dodge Hemi head, cylinder head, all righty? And if you go to there it is, see it? The evaluation tab, right there, evaluate. And look over here, look what comes out the other side. Center of mass, principal axes, principal moments, moments of inertia, okay? Just boom, comes right out. All righty? So no need ever to calculate these things. It is, however, essential that you understand what you're doing. You understand what they mean. And this is the whole purpose of this exercise. So what I'd like to do is quickly kind of examine these. This is right out of the book. And let me just tell you, the rookie error in using moments of inertia from tables like this is mistakes in recognizing and or choosing the moment of the body coordinate system. All right, when the cylinder. Let's just look at this real quick. See how the cylinder is organized? It's got a radius, it's got a mass, and it's got a cylinder of mass m, radius r, length h. And this is what the book doesn't say very clearly. Oriented thusly has the following moment of inertia matrix. Notice that the x-axis, ixx, and the y-axis, iyy, oddly are the same. 1/2 m times that, and that makes sense. Moment of inertia, if you spin it about this axis or you spin it about this axis, it's the same. Clear enough? And the third axis, the ZZ axis, if you spin it this way, you're going to get a different number, okay? Because it's like this. It's the difference between this and that. Clear enough? So the point is, when you bring in, don't just say a cylinder only has one moment of inertia matrix, okay? You have to be very clear about what you are designating, the problem designates as the body coordinate system axis choices. Ditto for the slender rod. How about it? Beckett, help us out here. Is this right? Does this stand the test of reason?
Yeah, it makes sense, especially given the cylinder from before.
Yeah.
We consider R to be very, very small.
Oh, you got to me there. How on earth can you justify that being 0?
R is super small.
Arbitrarily small. Okay, it's kind of. All righty. Very good. Well, that's that. We did the SolidWorks thing. Okay, and that's the end of that video segment, and we're going to start the next one. All right.